back and check your presentation. So yeah, where's yours?
Thank you for the introduction. And so I'm Wei Yan. So here I'm going to talk about the quarks and gluons inside the hadron and incerton vacuum. So we already know pretty well about the pervasive QCD, which is in the very high energy scale. We know the coupling is weak coupling. But then we also know that this theoretical framework doesn't work when you go to the low energy, which you only see the hadrons, you only see meson baryons, you don't see gluons and quarks. And we know that in that region, the only thing is we have the practical computational tool, which is a lattice QCD. But then the question is, then what is the physical picture behind this from non-pervasive physics? So today I'm going to talk about my research on this non-pervasive physics. So the first question is a non-pervasive perspective of the QCD. We know that in the low energy, there are three major symmetry dominate the QCD. The first one is spontaneous chiral symmetry breaking, so that we have the mesons. And the second one is a trace anomaly that tells us the origin of most of the hadron's mass. And also the chiral anomaly that tells us why the eta prime is so massive compared with other mesons. And as you can see, if you go to the chiral limit, which is the quark is massless, then the trace anomaly and the chiral anomaly, they are dominated by the QG square and the GG tilde, which is a global and scalar global and pseudoscalar group. Okay, so this is two important parameters. And also you see the spontaneous chiral symmetry breaking is dominated by the chiral condensate. So these are the operators used to parameterize the vacuum. Okay, so how to describe the non-pervasive phenomena in QCD? So we know QCD, it's a scale-dependent theory. So in the high energy scale, it's pervasive QCD. But when it goes down like around 10 GeV squared, around this here, then we know that some of the non-pervasive effect will start to affect the result, and especially when you go to the soft. So here, the incerton, I will introduce it later. So here, in the semi-hard, we know that the quark and gluon, they will couple to the incerton. And then when you go to the soft region, then quark will couple to the meson. And quark meson dynamics can be determined by incerton. And then when you go to further to the very ultra soft energy scale, you have the chiral perturbation theory. This can also be emergent from the incerton theory. So we can see the meson dynamics is also dominated by the incerton. So here is the picture of the incerton vacuum. This is the calculation on the lattice. When you deploy the lattice vacuum to the energy scale around 0.6 to 0.7 GeV, then you will see most of the gluon plane wave structure, they disappear, or become less dominant compared with this localized structures. And this localized structure, we call them incertons. So they are structures dominated by the size around 1/3 Fermi, and also their density is around 1 Fermi to the -4, which is a dilute picture. So in the non-pervasive region, instead of using the G square, we have a new parameter to do the expansion, that is the incerton density. And what is incerton? It's actually the tunneling event happening inside the vacuum. So as you can see, this tells you in this volume that how frequent the tunneling happen in the QCD. They jump from the topological Farquhar by the transition +1 and -1. Okay, so based on this picture, we build up an ensemble picture. This is the partition function. Directly, we can derive this partition function from the QCD path integral. And then we rewrite the gluon part into this random ensemble. N is probability, or we call it the instanton density distribution. And here describe the quark and instanton couplings. And this is the Feynman picture. So any kinds of QCD operators in this picture can be calculated by this expansion. As you can see, this is a density expansion. So that explains why in the low energy, we usually only see the quark dynamics, because describe the meson, they are majorly, we know it's quark bound state. And then also, when you use this chiral perturbation theory or any kinds of quark effective theory, where is the gluon? So here, give us a picture that the gluon dynamics or the gluon degrees of freedom is encoded in this density. And you say, okay, and you say the density is just a number. How can it describe the dynamics? So here, because it's ensemble, so the number fluctuates. So this fluctuation tells you what is the gluon dynamics in the low energy. So we have the G squared, GG tilde, which is the trace anomaly and the pseudoscalar chiral anomaly. So we have the distribution to describe these fluctuations, just like in the ensemble, grand canonical ensemble. And the number governed by the topological compressibility, and the number difference, which is a topological charge, is governed by the topological susceptibility. And first of all, what's a picture for spontaneous chirosymmetry breaking in QCD? It's just like the transition, phase transition between the conducting phase and insulate phase. This gray ball and white ball, they are instantons. And quark, when quark pass through the vacuums, they will scatter by the instantons, just like in the metal. And when they jump from one instanton to another instanton, they start to conduct. So when the density is enough, not that dense, but dense enough, then you will know that the quark can jump from one instanton to another instanton and keep conduct to the infinity and then disappear. And we know quark carries axial charge. So if axial charge disappears in the boundary, then that means the chirosymmetry is broken in this picture. So that's how we describe the spontaneous chirosymmetry breaking. So that means the quark condensate will no longer be zero. So we have the non-trivial quark condensate. And okay. So I will go quickly. So then this is the hadrons in the instanton vacuum picture. As you can see, this is how the quark interact with the instanton. And then you can write down the effective Lagrangian. You can use the effective Lagrangian to describe the meson dynamics. And you can get the meson spectrums correctly. And also go beyond that level, you can describe this is another effective interaction, which can help you describe the factor mesons and so stuff. Okay, so this all are coming from the instanton picture. So this is the remarks. We know the QCD vacuum, we have evidence saying that it's subelectral active around this 6.6 GeV. And it can describe the light meson dynamics and also for the light baryons, because those interactions can describe the dynamics between the diquarks. And also the gluon dynamics is also included in these pictures. So here we provide a solid framework to calculate the non-perturbative QCD. And this is all the result. It's fit with experimental result and lattice pretty well. So this gives us a very clear physical picture to describe the non-perturbative physics. Thank you.
Thank you. Are there questions?
Yes.
So are you saying that instantons generate the mass?
Yes.
Okay.
So we know the 95% of the nuclear mass is not coming from the Higgs, and it's coming from actually instantons.
Everyone in the back?
Yeah, so the question is, can I understand like the instanton is something we see on the lattice calculation?
Yes.
And the density and the scale of the instanton are also decided by that observation or measurements.
Mm-hmm.
So do we have some experimental evidence to show the existence of the instanton?
if these are evidence, but of course you will say this is probably not the direct evidence for the institute. But so far we calculate the energy momentum form factor, which is very important that recently people are interested in. And also this is a pressure inside the pion and the shear distribution inside the pion, and also the electromagnetic form factor. And this is the nucleon EDN form factors. So there are so many form factors we already calculate. Some of them is not available by the experiment. Some of them we already have the experimental data, and compared with those data, it's very consistent. So,
Okay, let's open again. Let's switch, and I think it's also, I believe. Yeah, ulcer and to open, we're gonna open. It's the first now. And okay. Whoops, sorry. Okay, great. All right. All set.
Okay, I'm Elsa Lopez. I'm from Guatemala. I'm studying in Mexico, the National Autonomous University of Mexico. I'm a master's student. I'm working with Aurora Courtois. And I will talk about the reconstruction of at least three-parton distribution function. First, let's talk about how we are reconstructing functions. Essentially, we are considering two main ideas. The first one is that the PDFs or whatever function can be described by these Bezier curves, which essentially is just a linear combination of these polynomials. And here you can see an example of a Bezier curve. The dashed lines are, okay, the dashed lines are just polynomials, and the black line is a linear combination of that. That's it. And the other idea is that the many moments could give us some geometrical information about the PDFs. That's it. Okay, and then the question is, given this parametrization and given some set of moments, can we reconstruct a PDF? The answer is yes, we can. And this is an example of that, where we are just reconstructing the Pion PDF, XPDF. As you can see, the dashed lines are the reconstructed PDFs consider many moments. For example, the blue one is considered only 2 moments. The another is 3 moments, 4 moments, 5 moments. As you can see, if you increase the number of moments, you get more accuracy. Here, for this example, we have an absolute error about 10 to the minus 7, which is great because we are not fitting. We are just consider the previous 2 ideas, only with this. Okay. And this is a great example. As you can see, there is a problem here because not always we know the moments. And as you can see, we need many moments in order to get a good accuracy. And then the next step could be include the data. Okay. Specifically, I'm working on trying to reconstruct the three-parton distribution function, usually known as EX or X, and people just call X dx. Okay. This has been accepted in many experiments like class at JLab. It's a higher twist. It's suppressed by a factor M over Q. It's defined by this. Okay. Why we are considering this PDF? Because the first 2 moments can be related with non-physical quantities. For example, the first moment is related with the pion nuclear sigma term, which appears in many experiments, in many nuclear experiments. And the second one is proportional to the valence quark number. That's great because we know this from lattice and we know this from theoretical things. That's it. Okay, then what is the next step is consider the data, the moments. Phantomosphicity essentially is just use the Bezier curves. And the end, we should get the EX reconstruct. And that's it. Thank you.
Questions further? Josh?
Is your curve for X times the PDF or just the PDF? Because
Here is X times.
X times the PDF.
Yeah. But works
I guess I'm talking about the slide before, the first plots you show. The first plots you show, maybe on your first slide. Yeah, these. Is this supposed to be X times the PDF, the combined one?
yeah, at the end doesn't matter because you could define the Bezier curve as X times. For example, you can put here X.
Yeah, I guess the reason I ask is because in the case of zero skewed, well, since it's a PDF, at X equals 0 tends to blow up towards infinity.
Yeah, that's a
Amazing.
problem, but we are working on because, and sometimes could be an infinity there.
Other questions? So, I mean, using the Beziers, you have in some ways a direct connection between some of the moments and some of the physical
Yeah,
things. So you can actually use those as direct constraints. Is that one of the advantages?
one of the advantage here is that using the Bezier curves, we have a lot of flexibility in order to get complicated curves. And we are using the moment like a constraints. That's it. The next step is not only consider the moments like a constraint, is consider the moments and the data. Okay.
And then actually on here, if you go back on the Bezier, so there, if you throw in a 1/x factor, I mean, that's sort of the modulation. So then you can do the small x principle.
Yeah, in principle, we can do whatever we want with this.
All right, let's thank us again.
Okay.
Next. So, let's see, so Granum, the screen mode. Okay, all right. And that'll forward, and the pointer is the top one. It takes it, yeah. Okay. Right, is that? Okay. Yeah, so. Let's see, yeah, that'll go back and then, yeah, that's a little, the pointer's the top one, it's a little slow. Okay, all set? Great.
Okay, so I'm Maham from Memorial University of Newfoundland, and today I will be talking about the quadratic and reducible two-loop level full electron-proton scattering with covariant approach. So what we do is basically the low energy precision physics, and that we achieve by calculating the higher order correction terms, which are up to the next leading order level, and we do this by using the covariant approach. And in particularly in this work, I will talk about the electron-proton scattering, full electroweak electron-proton scattering. And for this, we consider a longitudinally polarized electron which scatters off a proton target, which is unpolarized. And then we use the Feynman diagrams and Feynman rules to calculate the total amplitude scared for this diagram using the covariant approach. So now the question is, what is the covariant approach? So in this approach, basically, we split our Feynman diagram into two parts. So after splitting, we get an upper part and a lower part. So for example, in case of electron-proton scattering, the upper part contains incoming and outgoing electron, and solving this gives us the leptonic tensor. And similarly, the lower part, which contains incoming and outgoing proton, we calculate the amplitude scared, and that gives us the hadronic tensor. And then finally, we multiply these, contract these leptonic and hadronic tensors and get our total differential scattering cross-section. So in case of elastic electron-proton scattering, our hadronic tensor had this kind of form, where P1 and P2 are the incoming and outgoing proton momenta, and these H vectors, H1, H2, so on, H6, these are the hadronic structure functions, which we extract from the experimental data. And these are our QED and electroweak hadronic couplings with the form factors. So because we are considering the electroweak case, so we have a photon mediator which combines with this proton. So that's the coupling between the photon and the proton. And similarly, this is a coupling between the Z boson and the proton. And these are the corresponding electroweak, electric, and axial form factors, along with the Dirac and Pauli form factors. And these are our tree-level results for the electronic tensor, which are of the order of alpha. That is quite trivial. That's the form of the electronic tensor. These are results for the next to the leading order level electronic tensor, which is of the order of alpha square. And that is obtained by multiplying the tree-level electronic tensor with the sum of one loop level self-energy and triangular graphs. And that's the form of the next to a leading order level electronic tensor. It looks quite trivial, but in actual practice, we have 307 graphs for self-energy and triangular diagrams. And combining them all gives us this kind of electronic tensor, where these M factors are the electronic structure functions, which depends upon the momentum transfer. And they are written in terms of Poisson-Weltman integral functions. And we use the mathematical loop tools package to calculate them. And finally, these are our new results, QED electroweak, QED and electroweak next to the next leading order level electronic tensor, which is of the order of alpha cube. So these are new results. These are not calculated previously in the literature. And we do these, we calculate these terms in two forms. So first is by adding the one loop level self-energy and the triangular graphs and then squaring them. That gives us the correction factor, which is of the order of alpha cube. And second way of doing this is by taking the two loop reducible diagrams. So we split our two loop reducible diagrams into two parts. So one loop goes to the electronic part and the second loop goes to the hadronic part. And we calculate them separately and get our electronic tensor after that. And similarly, if we have a vertex correction and one loop, then we again split our diagram. So the vertex part goes to the electronic tensor and this one loop level goes to the hadronic tensor, and we calculate them separately. And we use fine arts and form calc as the base languages in order to calculate these electronic tensor structure functions. And another important thing is that we keep the mass of the electron throughout our calculations, which is usually ignored in the previous calculations. And finally, these are our results for tree level next to the leading order level and next to the next leading order level parity violating asymmetry in case of electron-proton scattering, which is on the y-axis. And on x-axis, we have the scattering angle theta, which is in center of mass frame. And we took the kinematics from the Q-week experiment. In case of Q-week, they measured the value of this parity violating asymmetry for theta 14.6, that theta is in center of mass frame. And the Q-week measured value is around minus 226.5 parts per billion with these statistical and systematic errors. And so this one is the measured Q-week value. And here the dotted line represents our tree level value. And again, we consider this angle 14.6 degrees. So our tree level parity violating asymmetry comes out to be minus 298.9 parts per billion. Our next door leading order level value comes out to be minus 239 parts per billion, which is quite an improvement. And similarly, if you consider our next to the next leading order level, parity violating asymmetry, it comes out to be minus 230 parts per billion, which is quite close to this Q-week measured value. And this is our calculation for next to the leading order and next to the next leading order level correction factors in case of this parity violating asymmetry for electron-proton scattering. Again, we consider the QV kinematics and consider this angle 14.6 degrees. Our next to the leading order level correction factor for this parity violating asymmetry is around 19.9%. And the quadratic level correction factor is around 22.5%. So there is around 2.6% correction factor, which we obtained when we consider this quadratic level diagrams. And if we consider all the diagrams like next to a leading order level, quadratic level, and two loop reducible, our correction factor comes out to be 22.9%. So the improvement is around 0.5%. So that's the formula for the correction factors. So this gives you an idea why including these higher order terms are quite important, because nowadays we have quite ultra precise experiments which are measuring the different kinds of like parity violating asymmetry. So that's why on theory side, we need to include all these higher order radiative corrections to improve our results. And finally, I would say that the work in progress is in order to include the soft and hard photon Bremsstrahlung cross sections. And our next goal is also consider the polarized proton and study the parity violating asymmetry effects in case of the electron proton scattering. And these theoretical predictions that we made will be important for many experimental programs such as QV, P2, electron ion collider, and Moiler for the background studies, which are all searching for physics beyond the standard model at the precision frontier. And at the end, I would like to acknowledge the support from Canadian Institute of Nuclear Physics and NSARC for supporting this project. Thanks so much.
Any questions? So you show, I mean, the next leading order, that was 239 versus, and then 230 at NNO. So the next leading order, that was sort of at the edge of 1 sigma. I mean, that was really, did I read that right? I mean, that was quite the next, yeah, it was a couple, keep going. Yeah, right. Yeah, so the 239 that's sort of at the edge, right? That's, yeah, that's sort of unsettling, but okay.
Yeah, so that's only the next one leading order level.
Right.
That's reduced. But okay, so that's minus 230, and this Mayer value is minus 226. So we still need to consider the Bremsstrahlung effects and the box diagrams. Those diagrams are missing. So
What's the order of magnitude of the diagrams at NLO?
oh, and then
So
yeah,
it's 307?
yeah, these are in total 307. So
Or NLO, that's for NLO?
NLO.
NLO.
Yeah, and only for like the self energy and the triangular diagrams. So we didn't consider the boxes yet.
All right. Other questions or? No, let's thank you again. So. Let's see, and it's every. Yeah. Try to click on the screen. All right, yeah, and is it, oh, yeah, on the bottom one of the verse? Yeah, and on the top one, I think you have to hold it. Okay, I'll use.
Hello, my name is Navpreet Kaur, and I'm working currently on the GPDs for baryon octets. So this is outline of my talk, and we know that QCD is the baseline to understand the strong interactions as well as to understand the internal hadronic structure in terms of the patterns. So it is always preferable to work in the Lorentz invariant form, and that we generally express in a 4-vector form. Which is the very crucial concept of a special theory of relativity. And in special theory of relativity, we deal with the Minkowski space. And Dirac proposed that there are 3 different forms in which the dynamical variables can be expressed in different forms, and they can be evolved along the different times and different forms. But the end results, we are getting the same. So we are basically use the light front dynamics. So we are going to use the front form. So in front form, the 4-vector notation is expressed as this. X plus component corresponds to the light front time along which our events will be evolved. X minus corresponds to the longitudinal space variable. X perp represent the transverse variable. And similarly, we can represent our longitudinal momentum as well as light front energy. So the reason why we are using the front form dynamics, there are 3 main reasons. Number 1, there is no square root factor. That means the calculation part is a little bit easier than other. Second, the vacuum expectation value is 0. That means there is no spontaneous formation and annihilation of particles. And the last one is the most of the fundamental quantities are kinematical in nature. That means they are free from the interactions. So these are the distribution functions we generally study. So GTMD, which is a multidimensional distribution functions. can be reduced to TMDs and GPDs, but I'm going to talk about GPDs only. So this is the correlator function in which we are having a quark field operators along with the Wilson line and the gamma matrices, which is sandwiched between the initial and the final state of a hadron. And this is the left-hand side of a correlator, and solving both the equations, we get H and E in terms of the overlap wave function form. So depending upon which gamma matrix we are taking, we are having a different kinds of GPDs. Corresponding to gamma plus, we are going to have an unpolarized GPD. That means we are going to have an unpolarized quark. H corresponds to unpolarized quark within an unpolarized a nucleon or a hadron. And similarly, if I talk about E, it corresponds to unpolarized quark within the transversely polarized hadron. So I'm going to talk only about the H and E GPD. So GPD is basically a function of three variables: X, which is the momentum fraction carried by active quark. Second is the skewness parameter, and third one is the momentum transfer between initial and the final state. In case of TMDs, we are having the same initial and final state, but here there is a momentum transfer and we are having different states. So DVCS basically as a golden channel to assess the GPDs. So a virtual photon interacts with one of a quark of a hadron, and then we will have a real photon and a final state of a hadron with a changed momentum. So GPDs can be reduced to PDFs if we integrate it over the T, that is the momentum transfer. And it is also a pathway to the form factors. And if we transfer our T to the coordinate space or in the impact parameter space, then we get the Fourier transformed form factors. So combining both, we can say that the GPD give us a 3D hybrid distribution having a 1D momentum space coordinate and 2D coordinate space or impact parameter space. So we can also get an information about the charge and magnetization distribution through the H and E GPD. So we have used a quark scalar diquark model. Basically, baryon is made up of 3 quarks. So what we are doing, we are considering one as an active quark and combining the remaining 2 quarks and label it as a spectator. So here the spectator will treat only as a scalar. I'm not considering any vector contribution for here. But if I talk about the complete solution, there must be a vector diquark also. So here we will have only the qualitative distributions, not the quantitatively it is going to be correct. So these are the light front wave functions. So these are the outcomes. H for U flavor, if I'm talking about. In case of lambda and sigma, you can we know that they are having the 2 light quarks and 1 strange quark. And the difference lies only in the masses. So if we look into the mass, lambda is lighter than the sigma. So we can clearly see that the distribution is more pronounced for sigma as compared to lambda. That means mass dominates in case of GPDH. And if we talk about upper and lower diagrams, in case of cascade, we are having a heavy diquark. Heavy diquark means it has a tendency to carry more longitudinal momentum fraction than the X. That's why peak is shifted towards left in case of cascade. Next for S quark. For S quark, again, if we move from up to down, the diquark becomes heavy, means spectator becomes heavy. So it's obvious that my strange quark will carry a less longitudinal momentum fraction than case of sigma and lambda. Next, GPDE, which corresponds to the unpolarized quark in a transversely polarized hadron. So here again, these quarks will carry a lesser momentum fraction as compared to the unpolarized hadron, but here the amplitude is more as compared to the HGPD. And similarly, we are having the plots for S flavor quark. Thank you.
All right, questions?
Why did you reconsider the zero skills GPDs?
Zero skills, actually here I am just considered the purely transverse momentum distribution. Means the difference in the initial and momentum space is the only the transverse, taking longitudinal zero, but I am working with skewness also and with vector diequark. It will be my next project.
Other questions?
Can you go back to the page that you have the quark scalar diquark wave function? Yeah, so my question is, how do you describe the scalar diquark here? Is there any?
Scalar diquark means I said that there are three quarks and proton. So
Yeah.
UD. So I'm considering UD as a spectator, which is having opposite spins.
Yes, so in here framework, you just don't treat the diquark and only treat that single quark in your theory.
As an active.
Uh,
Means it will
So
interact.
only that quark attend the interaction.
Yeah, the incoming virtual photon will interact only with the active quark, and the rest of will act as a spectator.
Thanks. Thank you. Let's see, and. Do this works. It's forward, back, and that's what it's called. Okay, one second.
So hi, can you hear everyone? Can you hear me? Yeah. So I am Sagotam Ta. I am from India, Institute of Mathematical Sciences. I work under Dr. Shantan Sharma. And today I will tell you about the instanton properties in the chiral symmetry broken phase of QCD and how we can implement in EIC. So we know for massless quantum chromodynamics, the symmetry group is
It's a little slow, sorry.
SU2 vector 2, and we are working in 2+1 flavor QCD. So the U and D are nearly massless and the strange quark is massive. And so the symmetry group is SU2 vector cross SU2 axial cross UP. And UA1, this axial charge is always symmetry is broken due to quantum effects. As we know, the U1 axial anomaly, the current is not conserved due to this relation. And this is known as the topological charge density, and this is the way this for due to this effect, the mass of the eta prime is much heavier than the other octet mesons. So this is one example, and another example is the spontaneous symmetry breaking of this axial anomaly, SU2 axial anomaly. So from the Banks-Kessler relation, we know that the chiral condensate is related to the eigendensity of near zero. So I will explain you. So if I say this Dirac operator psi I equals to lambda I psi I. So if lambda I is 0, then we say this is 0 mode. And if lambda is nearby 0, then it is known as near 0 mode. So this rho r 0 is the density near 0, the eigendensity near 0. So if it is non-zero, then the chiral condensate is non-zero and the SUA2 is broken spontaneously. And if we in system we have instanton and anti-instanton interaction, then it is non-zero. So that is one example that we should be interested in QCD instantons. So what are instantons? Instantons are nothing but and once the QCD vacuum is degenerate. And it is infinitely degenerate. And this is the 1 degrees of freedom minus 1. So if there are infinitely degenerate vacuums, so we can tunnel from one vacuum to another. So in Minkowski space, this tunneling picture exists, but if we go towards the Euclidean picture, this potential totally just flips and it goes to this. So we can go from this hill to this hill using classical path. We can go. So at very large time before we have zero energy, and at very large time in future we have zero energy. So these instantons are the similar in space to the tunneling solution. So they are zero energy solutions of QCD Hamiltonian, and they correspond to finite action solution. And so after that, so they are localized at some point x0, and they have some certain radius rho, and they have some color orientation. So how do they look like? You have seen already this picture. This is a picture of instantons, and anti-instantons are just popping out from vacuum and merging and again popping out. So it is one snapshot of QCD vacuum. So there are many techniques in lattice to detect these instantons. One is you calculate this quantity, the topological charge density, and you detect the peaks of this because it is localized and it had certain heights, and from that you detect the instantons. Another thing is in QCD you have index theorem, and from that you calculate the spectrum of Dirac operator, and from that you calculate the instantons and anti-instantons. But generating configurations in lattice with fermions is quite difficult because to detect the instantons you need exact chirality. But due to this theorem, we know there are 4 quantities. One is chirality, second hermiticity, third locality, and doublers. We cannot satisfy these 4 conditions in lattice. So we have to for that only in this operator overlap operator only exact chirality and index theorem is satisfied. So we have used this overlap operator and calculated the Dirac spectrum, and from that we are determining the instantons. Yes, so this is the spectrum of Dirac operator, and from that usually in Dirac operator there are no zero modes, means the lambda cannot be 0. But if we have instanton, the gauge background there are instanton, then the 0 mode is possible, and for that there is this wave function. And if we can see the peak, the location of the instanton, the gauge field, and the wave function is same. So if we calculate the density of the Heidegger side, then from that we can detect the instantons. So if there are 0 modes, purely 0 modes, means this size 0, then it is related to isolated instantons. But if there are near 0 modes, then there are interacting instantons and anti-instantons. From 0 modes, we are calculating the size distribution, means how the size varies between different instantons. And from the near 0 modes, there are multiple instanton anti-instantons. So we are calculating how they are interacting from near 0 modes. So this is one plot for pure gauge, and there are no fermions. So here this is the distribution we got, how the size is changing. This is the histogram, the probability density, and this is a dimensionless radius, how it is changing. So we are getting currently 0.4 Fermi, and in the first lecture you have seen that for instanton liquid it is around 0.3 Fermi, and it is a very preliminary result. So we have to take into account and discretization effects and large lattice size. And this is the distance distribution, how the distance is changing from pure gauge to if we include fermions. So there are large effects due to the period, like in the boundary conditions. We have to take into account, but they are too much preliminary, so we cannot rely on these results that much. So why instantons are relevant, how they are in DIS. So if you see this process, the electron is scattering and the proton is producing, from this side the proton is coming, and it is not directly interacting with the quark. It is interacting with the gluons via an instanton. So this instanton is just generating quarks, and from that quark one jet is producing, so we can detect by this forward jet, and the order of the, if we have three flavor fermions, 2+1 flavor, then there will be order of 10 partons. So from that we can detect experimentally is this process is instanton generated or not. So why it is relevant? Because as we know, at small Bjorken X, the QCD is totally dominated by the gluons, and if it is totally, and the density is very high, so it is non-perturbative. So we have to take into this non-perturbative instanton-like objects. So that's it. And in this instanton perturbation theory, if we calculate the cross section, the inputs comes the D row, the dense size distribution, and which I have shown before, and this is the interaction between instanton and anti-instanton. So we will calculate this from lattice and input this in this cross section and give some prediction for EIC. And so as in this DIS section, DIS processes, there are the proton virtuality is finite. That's why there is a limitation of size for instantons. We do not have to account for all possible sizes of instantons. So up to this size is relevant for. So we will measure that and give some predictions for that. Thank you.
Okay, thank you. Any questions?
Do anti-instantons have the same behavior as instantons, just opposite top
Yeah.
and charge?
Yeah, if the CP is totally is violated in QCD, then there will not be. But as CP is not violated, then they give similar results. I have also results for the different results for size distribution of instanton and anti-instanton, and the distance between two instantons and the distance between two anti-instantons. In this plot, I have shown you the distance between one instanton and one anti-instanton. If I go back, yes. This plot, it is a distance between one instanton and one anti-instanton. But I have plot that shows one distance between two instantons or distance between two anti-instanton. They show they say in the same region the peak. So there is no distinction.
No, it's.
Thank you.
Sure. Yeah, that's forward, that's backwards. Takes a little bit, the top ones. Okay.
So hi, I am Sayok and today I am talking about the axial charge product in the presence of gauge field. So, the QCD is the theory of strong interaction, and in the Lagrangian of QCD, this is the fermionic part where there is d mu, where the interaction between the fermionic and the gluonic part, and this is the pure gluonic Lagrangian. So, in massless limit, classically this axial current is conserved, but due to quantum effects, it is violated. And because of this term, G tilde. So this is actually E dot B in color space. So we can write it as a del mu K mu, where K mu is our currents. So from this equation, if we integrate along the spatial direction, so we get the net axial charge J50 can be directly related to the difference in the Chern-Simons number. So Chern-Simons number, we are calling it as the spatial integral of this K0 current. So from this relation, thus the axial charge of the chiral fermion tracks the change in the Chern-Simons number very efficiently. So, so this Chern-Simons number characterizes the QCD vacuum, which is infinitely degenerate. So here I have plotted the potential, which is the purely gluonic potential. And along this NCS direction, this is periodic. So we cannot go from one vacuum to another vacuum through local gauge transformation. So we can only change the Chern-Simons number by two ways. There exists tunneling solution which tunnels from this vacuum to this vacuum. We call this instantaneous, as we saw previously. So which is a zero energy and finite action solution of the gauge fields. But there are also solutions that crosses the barrier height through the transition through the barrier above the height. So this is called the Speleron solution, and because there is a barrier height, it has finite energy. It is finite energy solution, and also it is unstable because it resides on the top of this hill. And these both transition, instantaneous Speleron transitions, are topological solution of the gauge fields. Okay, so why these transitions are important? Because this electroic Speleron, this violet baryon number and lepton number, but the difference B minus L is conjugate. So it's violet B plus L, but the difference is conjugate, and this leading to CP violation in the standard model. We will specify the study of the dynamics of the QCD Speleron in non-abelian highly occupied phase of gluons. So we call it plasma phase. We will study the Speleron transition rate in this plasma phase. And for that, we use the overlap fermions, which has exact chiral symmetry on the lattice, and to construct the chiral charge in order to track the change in Chern-Simons number due to frequent Speleron transition. So here I want to satisfy and check that relation, and we construct this J05 on overlap operator. So this is the result for there is a single Speleron transition. So this red line is 2 times delta NCS. So it goes from 0 to 2 along time direction. So the delta NCS is changing 1 unit. So there is going from 0 to 1. The vacuum is vacuum. So we are going from one vacuum to another vacuum. And this blue line is the change in the axial charge. So it matches with the delta NCS as the relation shows. And here we perform the same simulation for the non-equilibrium case, where we start with plasma initial condition. So we start with where the gluon occupancy is large up to some momentum scale, and above that momentum scale there is no occupancy of gluon. So we start with that initial condition, and we time evolve through Hamilton's equation and calculate this delta NCS and J08. So because of this gauge noise, this reduces the efficiency of the tracking. But if we increase, we have done it for in 8 lattice size. But if we do it from larger lattice size, which we're gonna do, and smaller lattice spacing, it will follow quite well. So why these transitions are important, Speleron transition? Because it is explain the gluon saturation in this process. So here, as Sagatam explained, that in this process, if we calculate the cross section of this process, and it's become approximately pi rho square for r greater than rho. So rho is the average size of the instanton. So when we increase the r up above some rho, and the rho is constant, the cross section become constant, so it explains gluon saturation. So why Speleron is important in this process? So when there is a multiple gluons in the final state of this above process, then the Speleron transition become important, and to explain this gluon saturation. So that is why we have to calculate the Speleron rate very efficiently, and we are doing it on lattice so that we can calculate the rate. Thank you.
Questions?
Two, I just have a naive question. Why do you no, the slide before. Why do you rescale the axial current to say it's just -2 times the number of flavors times the vector? I guess it just, what's the point of rescaling?
So here,
Yeah, yeah, the far left and then the far right side. They seem equivalent just by a factor of -2 NF.
so I didn't get.
But why do you rescale? Why do you pull out the -2 NF?
Oh, here. So, so there is a, okay, so the form of the K mu. So there is a form of the current. So, and it explains this NCS. This NCS is topological charge. So when there is a mapping solution, there exists some winding number. And let's here the mapping is from S3 to S3. Okay. So in that case, there is a winding number and the winding number there is a form of the winding number. Okay. So this NCS is that winding number. So I am putting that winding number form in the NCS. So that to do that, we have to put out this factor of 2. That is why
I might note the Simons in that is the same Simons. He was a professor here in the math department where he went out to the finance world, and that's the same Simons as the building next door. Yeah, that's quite local. So other questions? No, let's thank Sarek again. So yeah, and big one moves it forward. Yeah.
All right, so as you can see, I'm gonna be talking about TMDs, not instantons or anything like we've talked just now. And I'll try to be quick so we leave early.
So that's right.
So everything I'm gonna say very briefly, obviously, is based off of these papers, the first 2 of which I've collaborated with my advisor and other collaborators. And so we've seen this formula about when Alexei was lecturing of how a TMD normally is presented. So we have the first term is so-called the OP expansion, which is only valid at small bt. This piece you can calculate from perturbation theory. The second term is just the evolution factor. So it basically tells you how to go from one scale to the other. And also, if you write it in this term, this is also calculable in perturbative QCD. And then, of course, TMDs are non-perturbative objects. So normally you just have a piece where normally people like to write it down in terms of G functions, those 2 G's in the exponent. But the point is that it's something that is non-perturbative because it describes the large BT part of the TMD. Now, this is all good and it works. It's normally referred to as the CSS formalism, Collins-Soper and Sturman. So it doesn't have any, I mean, it works in practice. You can show that the TMD you can rewrite in this way, but when you actually use this sort of parameterization in phenomenology, you have sometimes some problems. And the problem is that when you basically truncate the part that you say, okay, I trust my perturbative expansion, and then at some certain point, I do not trust it anymore, which normally is done through a Bmax cutoff, basically just split the space in 2. That Bmax essentially leaks into your prediction. And here is just an example. So this in principle should be 1 line if it was Bmax independent. Again, the Bmax is just an auxiliary parameter which your results should not depend on. But for example, here you see that it depends a lot. The shaded curve should be just 1 single line, and it's definitely not. And here I'm showing the series differential cross section, the TMD part of the series differential cross section. On top of it, you also have other problems of matching regions, which essentially you have descriptions of the full cross section given by two different factorization theorems, and they should match, but they don't really quite well. And also some pieces don't match at all, like these two curves should be on top of each other and they are not. So the point here is that everything is formally correct, but when you implement it, it's not really. You have to be careful, and these problems are known. So on top of it, you have dependence on these parameters that you basically spoil your predictive power. So these are some big problems because if you do that, you're not really sure whether your assumptions, your hypothesis like leak into the prediction, into the fit, because in the end you have to fit these things and you don't really know how to manage the error that you make. So this is the standard approach. What we've done is essentially something else. But before, let me talk about what are the problems that people tackle in the standard approach. Because when you study TMDs, you always find if you remember the OPE part, the first piece of the parameterization there, I told you it comes from perturbation theory, and that piece has a lot of logs. It's just a sum of alpha s and powers of logs. And the logs all have this form. So log of mu times bt divided by this number. Now, logs are divergent both at bt equals 0, so at, and the two limits, bt equals 0, bt equals infinity. Normally, these two problems are tackled together using, so essentially the large bt problem I already said is just simply, you simply put a Bmax or a cutoff and you don't have large logs, at large bt. But when you go at small bt, that is actually a different problem. And and you can solve it by using renormalization group equations. So you just change scale, a scale that essentially you choose a mu that goes like 1 over bt so that your logs get killed. And all the rest is in the exponent of the evolution factor. So you essentially resum all the logs in the exponential factor. But it's an exact resummation because you know how to solve the equations. So what I wanted to just highlight is that these seem the same problem because they appear in the same log, but they're conceptually two different problems, and you can't tackle them in two separate ways, not together, which is what people do normally. So what we've done is essentially that, and the formula is simply to get what we already know from the theory. So if you have the OP expansion, so whatever you know from perturbative QCD, and you also impose the fact that your TMD, if you integrate it over the whole transit momentum, gives you the collinear counterpart plus perturbative correction, which you can calculate, then you don't need to impose input any Bmax dependence. You do need to obviously do the RG improvement, so the evolution, but you definitely don't need to do that. And so that plot that I showed you earlier, I don't know how to go back with this, but that blue plot essentially is not there. You just don't have it. You will have a line because it's not dependent. We just don't have this Bmax dependence. But everything is conceptually the same. So if you do that, and we call it hydrostructure-oriented approach, but essentially is still CSS. It's just that we add the constraint that you already know from perturbation theory. And in fact, Alexei is not here, but he also recently published a paper where he generalizes the integral relation to any moments of the TMD. And we've done the same. Sorry, I went back. Can you go back once, please? So if you do that, and this is just an example of the parameterization, imposing the integral relation, you fit your data. This is just low Q data. And then we try the formalism, try to predict higher Qs. So we just fix everything at small q and just predict high Q. We don't fit all together. Everything turns out to be quite well. And these are these are post-dictions in a sense because we already have this data. It's quite old of Z boson production. But with just 3 parameters, no Bmax dependence, and by the way, everything was just a leading order in alpha S, you get decent results. And this was just a test for the formalism. It's not a global extraction. We don't claim that, but everything turns out to be pretty well, and there is no, all the errors are under control. So I'll just skip the summary and thank you.
Thank you. Any questions?
Right.
Okay, all right, thank you. And last but not least, Ryan is our final talk of the session.
Hey everyone, I'm sure you're sick and tired of calorimeters. You probably got a lifetime's worth of them here, but one last time, let's do it again. So yeah, I'm Ryan. I'll be covering the 0-degree calorimeter that was covered yesterday. And I'll be investigating its performance via graph neural networks. So just for some context, this detector, which is on the bottom right here, it's one that our group designed. If you remember, Alex was like, I have some friends from California that designed it for us. That was us. So it's we actually had 2 detectors in Epic. This other one, the insert, that was also mentioned in another presentation. They're both very similar in design. So who wants to review hadronic showers yet again? No? Too bad. Okay. So hadronic showers, they have 2 components. They have an electromagnetic component and a hadronic component, which is on the bottom left there. I don't dare do this. No, okay. It's on the bottom left. So basically you have your incident particle coming in and it will split into 2 different components, the electromagnetic component, and that component usually has a higher energy than the other component, which is the hadronic component. And this is seen here on the bottom right. So basically the hadronic component will have a very wide energy spread and very low energy compared to the electromagnetic portion. And that is a problem because that basically deteriorates your energy resolution in your detector, which is basically how well you can differentiate energies of particles. So like if you have a, I don't know, 1.1 GeV neutron hitting your detector, can you differentiate it from a 1.05 GeV neutron? That depends on your energy resolution of your detector. So you can mitigate this effect using specific design choices, but that imposes very strict requirements. So you can use tungsten, for instance, but tungsten's very expensive and it's, yeah. So people tried to mitigate this using various approaches. So there's 2 approaches up top. I'm not going to go over them from CERN and Calais. There's also some machine learning based approaches, which is what I'll be covering. And this was heavily done in Atlas, and or basically this project has some of those people from that project for this. And one thing I want to emphasize is that all those methods that were done post-experiment, like they designed the detector, all the data was taken, and then they applied these methods. Something that's interesting about ours is we're doing it during the design phase. So basically, machine learning is having an effect on how these detectors are being designed, which I think might be a first for, I guess maybe the newer LHC experiments, but the first major experiment that machine learning is employed from the get-go. So what I'm actually doing, so I basically simulate our detector, which is on the bottom left there, not super pretty, but I basically just fire in single neutrons into this detector, and I want to see what the energy and the angular resolution is of this detector using graph neural networks. So basically, the graph neural networks are going to predict the energy of the incident neutron and the angle of the incident neutron. And then on the bottom right here is just a small event display of what the hadronic shower would look like, which is a little messy. That got compressed. So basically what we do is I take the data from the calorimeter and I represent it as a graph, this is like the 4th image from Google Images or something like that. I basically just take all the cells from the calorimeter and put them in things called nodes, and that encodes the energy and the position of the cells, and then I connect them to nearby cells. And basically what that will do is our model will basically learn how the shower develops within the detector. Like it'll say, oh, this node here is connected to this other node here, so that means like the shower is nearby. And basically the machine learning model will be able to weight the different cells and mitigate this hadronic and electromagnetic problem that I showed before. And then also angle. So I'm not gonna detail everything here. The panel I want to focus on is this top one. So basically, I'm not gonna dare with the laser pointer, but these circle points, these open circles, those are basically, you just take all the energy in our detector from simulation and add them up, and that's an energy resolution Earth, and then you get the energy resolution from that. And if you compare it to that brown dotted line, that's where we need to be by like at a minimum in order to like barely satisfy all our physics requirements. So you see it's fine, but then when we apply our graph neural networks, which is these solid blue points on the bottom, you see that we kind of just blow the energy resolution out of the water. And then there's some other comparisons too. Basically, it does really well. And then we can look at the angular resolution too. And so I'm not going to go through all the points, but basically these three sets of points are just angular resolution obtained using different methods. And then the bottom one, which is these squares, it's the angular resolution using graph neural networks. And you see, again, a major improvement, especially at lower energies. I think that pretty much brings me to my end. So what are the takeaways from this? We can basically use machine learning to improve the performance of the detector. And it gives insight into how well we can measure physics processes. If you remember Alex's presentation, he had this lambda decay that went into neutron 2 photons, and he said that you really need good neutron angular resolution in order to reconstruct everything. And graph neural networks allows us to satisfy that very easily. And then again, I want to emphasize doing this during the design phase, we can basically optimize the detector design or to measure all of these physics processes. Yeah, that's it. Thanks.
It's, yeah, interesting to see they're doing this beforehand. I mean, like, issues is liquid argon, and then, Zeus used uranium in part to compensate. So,
Yeah.
so it's
Pretty cool. Yeah, it already had like effects in it too. Like there was a detector that had tungsten in it, and then we showed that hey, using these graph neural networks, you don't really need the tungsten, and now it doesn't have tungsten. Like, it just saved us a bunch of money.
expensive.
Yes, it was like $1 million decision based on this.
Any questions? If not, let's thank Ryan and all the speakers. And yeah, so you made it to the end. Congratulations, you're still standing. As I said, it was quite a busy schedule. So we have the barbecue downstairs. According to my magic app, it says the rain won't start till about 7. So hope that's correct. I could use some volunteers, all the cookies and things like that. I guess not the bagels, but the cookies we're going to take down. And if you want to take some bagels or whatever you see in there for tomorrow or your trip, go ahead and grab it. Everything has to go. But we'll see you downstairs at the barbecue. They're serving my favorite brand of beer, which is free beer. But my brother's down there on the grill. So hopefully we'll get them grilled before the rain comes. So thank you again and have a safe trip home. And that's an equation. We'll see you at JLab, at Brookhaven, or CERN, or somewhere in between. So take care.